Hello everyone. Today I want to talk about computers and data representation. If you've ever taken apart a computer, you've probably seen a motherboard. Looks something like this. There are all sorts of different types of motherboards. Typically on a motherboard, you can't see the CPU. However, you typically can see the memory. Actually, the memory would go into these blue slots over here. And of course, on the back of the computer are all the I/O ports that allow you to interface to, keyboards and monitors, printers, speakers, microphones, all those other kind of fun devices. The really bad analogy for a computer is to call it the brain. Of course, in reality, brains don't work at all like computers, but it works as a rough analogy. It does decide everything that goes on inside the computer. It is the kind of the master controller. And of course, CPU stands for Central Processing Unit. Most of what's going on inside that CPU are millions, actually billions of transistors, which are switching voltages on and off. And as we'll see, that's what we use to represent information. Now, on the back of that CPU, you can see that there are copper pads. And so those connect to corresponding socket in the motherboard, and each of those lines is able to transmit basically a single bit of information at a time. We'll talk about what that means. But those are electrical connections that turn on and off, and they're able to send information. The motherboard send information to the CPU, and the CPU will send information out to the motherboard. Now, one of the elements of a computer involves memory. So memory actually stores information as an electrical charge. It can be read or written to. This is the kind of analogy of a short-term memory. Information is basically forgotten once the power is removed. And again, just like on the CPU, we've got these electrical connectors on the bottom here, actually on both sides of these little circuit boards, and they connect to the motherboard over what's known as a bus. And what the CPU does is it sends an address, turning on and off voltages on some of these connectors at the right time, picks a particular number, and then that particular number, which is known as an address, that points to or selects a particular byte in memory. And we'll talk about bits and bytes. Memory can be written in larger chunks than that, but the minimum amount of information you can send back and forth from memory would be a byte. There are connections that allow you to do I/O, input-output, transfer of information to and or from a device. So as you're typing on the keyboard, you're sending information to the CPU. The CPU, when you're looking at a monitor, looking at the screen, the CPU is sent output to that display so that you can see that information. Hard drives also a type of I/O. The network cards will also send and receive information as well. But again, I want to stress the point that we represent information in the computer in a number of different ways, but for the most part on the motherboard, we're talking that the presence or absence of a voltage. And on is represented by a 1, and off is represented by represents a 0. Now, those could also be, the on could be a true, the off could be a false. Generally, though, so that's really saying a low voltage or a high voltage. Of course, we're not talking about high voltages in this case. Actually, the voltages using a computer are actually fairly low. In fact, they're actually have dropped over time. They're originally something like the high voltage was 5 volts. And that is slowly skipped down, and 1.8, 1.2 volts. You might have seen that in some cases that's actually a selectable voltage on some of the graphics cards that help you to overclock it. Now, it's important to note, while we know inside our computer we're able to play videos, we're able to play sounds. We're able to access the internet. But in no time are there are no actual videos stored. There's no actual characters stored inside the computer, technically. There are only representations of those items, and those are represented as voltages or charge. Physical hard drive, that could be a magnetization. Inside a solid state drive or a flash drive, it's actually a charge inside a solid state device. CD-ROM, CD, DVD, Blu-ray, those are stored. Information is stored as the presence or absence of a physical spot on that particular device. A very, very, very small spot. So we want to start talking about some of the ways that we can measure or define a computer, and the ways that information is represented. So one of the key things there is a bit is short for binary digit, and it's a single place, so a bit can be either a 0 or a 1. You might think by itself it wouldn't be worth a whole lot. Let's say, for example, I had a computer that simply turned the furnace on or off. Could have a thermostat device, and it could simply output a single bit, turn the furnace on or off at the right moment, and that certainly has value. Or something even crazier, like if I could create a computer that could tell me which stock I need to buy at a particular day. Should I buy this stock? Yes, no. Should I buy this stock? Yes, no. That could be very valuable, assuming you get that to work. But the thing is, we generally, though, we take bits, again, a 1 or a 0, and we group them together, and that grouping of bits allows us to represent many, many other things. If we take 8 of those and group them together, that's referred to as a byte, B-Y-T-E. Now again, a byte, 8 bits, 8 binary digits. Single bit can only represent a 0 or 1, but if we group them together with 8, we end up with a 2 to the 8th power possible values, which actually allows us to represent 256 possible values. Now note that that's if we're using what's known as if we're using a signed value. Let's say we want to represent a number, an integer value, and only positive values, which would be an unsigned value. We would say that what we can do with that is we can represent 0 through 255. So again, that we say there's 256 possible values, but again, that includes 0, of course. And as we said before, we're talking about memory. A byte is the smallest addressable memory amount. And that is, of course, a common unit of memory storage. But then when we group even larger amounts of bits and then bytes together, then we actually use what's called metric units, like kilobytes, megabytes, and gigabytes, and those are all powers of 10. Those are used for disk storage. Bytes can also be grouped into powers of 2, which of course makes sense internally with the computer, because basically everything internally in the computer, as we said, everything's represented by a bit. The connections on the motherboard and in memory are each of those individual connections represents a bit. So we're going to be kind of forced to do things in powers of 2. Now that's represented using what's called kibibytes, and of course you can see the different units down here. Kibibytes are actually in powers of 2, and that's usually used for memory or anything internal. Now, so disk storage basically uses different units than memory does. Now, in the old days, a kilobyte actually was 1,024 bytes, but the new standard that has come out. And again, if you go out to buy a hard drive, you will find that they are using kilobytes as 1,000 bytes. So the universal standard these days, even though again it used to be a different thing, someone asks you, what's a kilobyte? That's 1,000 bytes. It is not 1,024. That's actually a kibibyte. A kibibyte is 1,024. And here's all the different units: kilobyte, megabyte, gigabyte, terabyte, petabyte, exabyte, zettabyte, and yottabyte. And those are all powers of 10. Again, just like the metric style power of 10. And the powers of 2 units, again, that would be used for memory. That would be kibibyte. Oh, and also notice too the symbols here. This is KB, this is KIB. And we also have mebibyte, MIB, gibibyte, tebibyte, pebibyte, exabyte, zettabyte, yottabyte. And of course, while the differences, are fairly small, when you're looking at between a kilobyte and even a megabyte, 2 to 5% difference there. We start getting these larger units, it actually becomes much more significant. Again, because of the difference between the powers of 2 in that case. So we can have, as I was mentioning, we can represent a variety of things with those individual bits. We can have unsigned integers, and again, that's a positive whole number. We can have a signed integer, which represents the positive and negative whole numbers. A floating point number is a decimal or fractional number, and then we can also represent characters, and we can use the ASCII character set. There are other ways to represent information. For example, we actually also represent images, and there's ways to represent that as bits. We won't go into that right now. Well, images, video, sound, all those things get their own kind of representation. But again, ultimately, inside the computer, we're still only talking about on and off voltages, transistors turned on and off, or charges. The information is actually stored in memory as electrical charge. Now, what can I do with that byte, or 8 bits? Well, I can represent an unsigned integer, as I mentioned, from 0 to 255, and in binary, that would be 8 zeros all the way up to the maximum all ones in binary. Or we can represent the signed integer, where we have a negative 128 to 127. Now these again, they're the same bits, but we're kind of giving them we're assigning them a different representation. Now note that in the case when the leftmost, or the highest, the most significant bit here on the left-hand side, when that is a 1, that's how you know that you actually have a negative value. And then also important thing to note that an even number would have the least significant bit would be 0, and an odd number, the least significant bit would be 1, because the representation of those of the rightmost or least significant is basically the value of 1. Now, well, theoretically, you could represent a floating point value using a byte. The only standard ways of doing that require a 4 or 8 byte value. We can also represent characters as ASCII values as well. Now we're going to be working with inline assembly. So in order to do that, the way inline assembly works is you actually use the variables that are set up using C data types. Now there are a bunch of different types that represent a whole bunch of different things. The CHAR is short for character. That's a 1 byte, and that's an ASCII character. And you can look up in Google and what an ASCII chart is. It's supposed to be chart. And I'm sorry, that's an ASCII character. You can look up an ASCII chart to see exactly how those things are represented. But basically, each number in that 1 byte is assigned to a specific character. We can also represent a float or floating point. As I said, there are no there's no standards for representing a byte as a float, but we can do 4 and 8 bytes. This is how we actually represent an analog value. Now, of course, integer values, an integer value would represent whole numbers, but we can represent fractional numbers. So something as small as 1.8 times 10 to the minus 38. So basically, if you put 38 zeros in front of that value, obviously you have an extremely small number. But then you can also represent extremely large numbers, such as 3.4 times 10 to the 38. So again, add 38 zeros onto the end of that number, and you've got an extremely large number. And of course, those can also be positive and negative values. Now, and we can use a double. We can throw, instead of using 4 bytes, we can use 8, and then we can create even larger numbers using a double. So up to a number that has 300. I'm sorry, a number that is to the right of the decimal point by 308, or a number that has 308 zeros after the decimal point. Before the decimal point. Now we can also, again, an integer can be 4 bytes, and a signed integer. So again, we say signed. We're saying, so let's represent both negative and positive values. Basically, we take this unsigned value and split it into positive and negative. And again, if the most significant bit in that case is a 1, then that's how you know that it is a negative value. So, and as you can see, we can represent extremely large numbers in this case. Now, there are also smaller representations. 2 bytes is a short value that has 65,536 possibilities, so 0 to 65,535. And we can also say, we can take a long value and basically use a representation with 8 bytes, and then we can create a much larger we represent the numbers from 0 to 4 billion plus in this particular case. So all data types can also be defined as arrays. So all the items on this chart can also be represented as arrays. So you can kind of create, but if you take a bunch of characters and create an array out of them, basically we're saying let's take each one of these and then put another one right after it, and then we can basically index or use pointers to locate the individual bytes that are part of that array. It's actually a one-dimensional array is what we can create. So we're kind of creating a list of those items is what we're doing. And again, we can do that with any of these items. A list of characters is typically referred to as a string or an array of characters. A string is a one-dimensional array of characters. I mean, and we can do the same thing with all of these different data types. And how do we do that? Well, in C, we simply put the data type followed by the variable name, and then we put open and close square brackets. And you can assign the values. For characters, you can represent that as a string. Or in this case, I'm sorry, we're initializing it, but then we can also create an empty array as well, simply by specifying the number of characters that you would like in this case. In this case, we're simply saying just use the number of values that that are used in that particular string. So we'll have hello is 5 characters, and actually there's also a hidden character that indicates the end of the string, which is the value of 0, which you don't see. So this would actually end up being a 6-character string. You would not have to deal with that when you're defining something like an integer array. And so here's an example of creating an empty integer array. Again, int followed by the name of the int a would be our variable name in this particular case, and we're saying give us a 4-element array. Or we could again initialize the array using this format, using these curly braces. And again, you don't have to specify the size in that case, because this is obviously going to be a 3-element array. And these could be any length. Now, if you're working in Visual Studio to display information, kind of might not be terribly obvious, but Visual Studio will generally have some sort of default format, which I believe is generally a decimal format, base 10. But you can also, generally you can right-click on a window that's displaying information and specify that you'd like to see that in hexadecimal. Hexadecimal is usually best for displaying memory addresses because of its compactness, and also because it closely corresponds to binary. And just to show you how that works, so in base 10, we can go from, say, 0 to 15, and in binary, we would represent that by 4 bits, which, and actually 4 bits is referred to as a nibble. So yeah, 8 bits is a byte, 4 bits is a nibble. And so you can see then how in hexadecimal, actually a decimal and hexadecimal correspond exactly to each other all the way up until 9. But then when we start to get to 10, you know, hexadecimal is base 16, so it has 16 possible values, 0 through F. And so that when we hit 9, we switch over to A, B, C, D, E, and F. But binary, again, base 2, again, that means that there can only be, we're only using bits, so each bit can only be a 1 or a 0. And again, by grouping them together, we can create larger values. So the rightmost column, and I'll show you in the calculator here real quick. The rightmost column represents the value of 1. Then when you move over to the left, it becomes twice that, 2, and then the next one over is 4, and then 8. And what you'll notice, if you pay attention to the pattern here, this first this rightmost place here, it's, you know, again represents 1. It's changing its value every time. So every, you know, we go 0, 1, 0, 1, 0, 1. Now, but the place over to the left-hand side, when we count up, is changing every 2. So 0, 0, 1, 1, 0, 0, 1, 1. And then the next place is changing every 4. So zeros, 4 zeros, 4 ones, 4 zeros. And then, of course, the next value is changes every 8. So all zeros, then all ones. I'm sorry, 8 zeros, and then 8 ones. So now, if when you're using inline assembly language, you want to access a C variable, you simply use the name. So in this particular case, we're using a move instruction, and we're saying let's move the short value that I have here, so a 2-byte value, move that into the AX register. It's absolutely key that the type of the variable has to match the destination. What does that mean? So the size, basically, so the size of the variable has to match the destination. Short is 2 bytes, An AX register is also 2 bytes, so that works without a problem. We can also do, we can move a value into, note again that it's always instruction, then say basically destination and source. In this case, we're just saying move. So we're going to move the value that is located in my short, and we're going to move that into the AX register. In this case, we're saying let's move 1 into the myInt variable in memory. In this case, we're saying let's move the myInt value from memory, which is an integer 4 bytes, into the EAX register, and that EAX is of course 4 bytes. It has to be the same value in order for it to work. We can also use other instructions as well. Add, subtract, all those type things. And again, in this case, what we're saying is take the myInt value and add 1 to it. Now we can also address the we can also address the C variables. We can access the C variables using an address instead. So the LEA instruction allows you to get the actual address of the variable. And remember what I said about memory. Memory is basically a one-dimensional array, and we store information. And the smallest amount we can access is a byte. So an address is a number that points to that particular byte in memory. Now, in this case, in inline assembly, Microsoft only lets us do 32-bit instructions. Well, that means our memory addresses must be 32 bits. So those registers, 32-bit registers, always start with E. So if I wanted to take the address, so that's the number that points to where that particular byte is located in memory, and move that into the EAX register, that would give me the address of that value, not the actual value. So then I could use another instruction to actually access that particular value. And we could also load that. What's commonly used for pointers like that for loading information into memory, or I'm sorry, loading the address of something in memory, is generally the ESI and EDI registers, but you can use any register if you want. The ESI and EDI registers can't be broken up into smaller sections like the EAX, EBX, ECX, EDX registers can. Now, I was saying that I wanted to look at the calculator to kind of show you some of these representations. This is very handy for converting values between bases. And this should be standard in Windows, even though different versions of Windows have slightly different versions of this program. Generally, when you start out, when you open this calculator the first time, it's in this standard mode. So you won't see any of those base values until you go over here, click, and select the programmer version, the programmer mode for this particular calculator. And again, over here, so I have hex, which again, hexadecimal, decimal, octal, which that's actually base 8. So hexadecimal, again, base 16, decimal is base 10, 10 fingers, base 10, octals 8, binary is base 2. So then also the thing you should note here is that this also starts out in quad word. And I'll show you what that's for when we switch over to binary. But what you can do, note that decimal in this case is selected, so I can put in, say, 25, and it will immediately give me all the different the decimal, octal, and binary equivalents for that particular number. So the hexadecimal version, the hexadecimal equivalent of 25, decimal 25 is 19, and the binary version would be 0001 1001. So you can also see why you would probably want to use hexadecimal, because it become very tedious trying to do everything in binary, and it just takes up a lot of space. Now, of course, we can, everything happening here is all set up for decimal, but we can select one of these others, and you can actually work in the calculator using one of these other bases. So if I want to enter something in hexadecimal and convert it, I can do that. So let's say maybe I want 1A hexadecimal, that's 26 in decimal, and is represented by this particular value in binary. Now we can also, then I can click also over here on binary, and I can start typing, doing math basically only using the ones and zeros. Now, so if I were to enter, so I can clear this just like it. So what happens is that these other possible values get grayed out. So if you can notice, for hexadecimal we've got 0 through F. For decimal we've got 0 through 9. Octal we've got 0 through 7, and binary we only have 1 and 0. And again, I can enter a number. And so that number 1001 is actually 4 in decimal, and then I can multiply that by another number 10, which is 2 in decimal, and that's going to equal 1000, which is actually 8 in decimal. Now, another handy thing is this. I'm going to talk about what this Q word and what this button here is. There is a bit toggling keyboard, so maybe if you just want to play, this is useful if you want to just basically play around with individual bytes. And the Q word is an indication of the number of bits and bytes that we've created. So Q word stands for quad word, which would be 8 bytes. And we can switch that to D word, that's double word, 4 bytes. Word is 2 bytes, and byte, of course, is a single byte, 8 bits. Now, so if I switch, so you can see what happens here. And so this bit toggling keyboard, if I'm in byte mode, it's only allowing me to see 8 possible bits, or 1 byte. Now we switch back quad word. Again, that's 64 bits. D word, 32 bits. Word is 16 bits, and of course, again, bytes. So, and this is getting very useful. You can go in here and start toggling these things. I clear all these. I just set the first bit to 1. I'm going to get a value of 1, and of course, all these are going to be 1 in that case. Now, if I flip then on, let's say, turn that back off and turn on the second bit only, that is represents the value of 2. So what these things are really is these are powers. They're always powers of 2. So this would be the first bit is a power is 2 to the power of 0, which is 1. So that could either be a 1 or a 0. And then this is 2 to the first power, which of course is a value of 2. So if that bit is on, its value is it represents 2. And over here we can see that this particular bit has a value of 4, and that can, so that's 2 to the power of 2, and that power of 2 thing increases as we move over to the left. So let's say we go over to so this is the 0th bit, and then we come over here. This would end up being 5. Well, really technically that's this really technically is really the first bit, but again, they're doing it this way again to do that power of 2. So we 2 to the 0th power. It's actually calling it the 0th bit, but really we are really that's first bit, second, third, fourth, so on. We come over here to the 7th bit. We can see that that has a decimal value of 64. And now, of course, something strange is going to happen here. When I turn this one on, you'll notice that that as I referred to previously, when we're using signed integer representation for a byte, we turn that particular bit on, it becomes a negative value. So that's why the decimal value is negative 128 in this case. So what we're doing is we're splitting the possible values into 2, and so if you wanted to see what that would represent, we could simply so what we're saying is the calculator itself is always viewing those binary values as those binary values as a signed integer value. So now if I were to enter a 0 up here and then kind of show you, now we can then see that turning on this 8th bit over here from the left, that actually represents 128. I turn all of these bits on in that first byte, its value is 255. So again, if you refer from the slides, we're actually going from 0 to 255. Now, and then of course, again, we can just keep going, turn these things on. Each time I turn on one of these bits, it's the next power of 2 is being turned on. But again, now I'm in binary mode, so everything that I do, if I try to actually enter another number like a 4, it doesn't actually let you do it. You can only enter ones and zeros. So this can be very useful for doing any kind of math and doing conversions between the different bases. Now, what's interesting though is let's go back to working with a byte. Now, what if I switch this back over here? And so I can add, so if I got 0, I can add 1 to it, and I can keep. You can see what happens when we just keep incrementing. We go from 0 to 1 to 1 0 1 1, and so on. We just keep going up, and you see that consistent pattern that's happening. But now again, so I've got a byte here. I'm only allowed to have a byte, again, 8 bits. So what happens when I start to what happens when I run out of bits? So let's enter instead 8 bits. If we switch back and forth here, you see that those bits are all set to 1. Now it's telling me that value is a -1 in that case in decimal. But that, like I said, is a signed value, and an unsigned value in that case would actually be 255. Now, if we were to add 1 to that, look at what happened in that case. I had a whole bunch of bits, and I added 1 to it. And it went to 0. What's happening there? Well, the bit representation. So this, these, when you have all these bits on, and we go to increment, we add a 1 to it. We're actually saying, well, that would actually be 1 0 0 0 0. But the thing is, in this case, we only have 8 bits. So we have, in that particular case, we've created what's known as an overflow scenario. we've run out of possible bits. So what ends up happening, it just ends up wrapping around. So our value in that case, which would be 255, unsigned, ends up wrapping back around to 0. Basically, because we kind of ran out of space. You can also have what's an underflow scenario. You can simply clear this out. If I were then to switch back over the regular calculator, if I take 0 and I subtract 1 from it, it basically underflows or kind of wraps all the way around back to that all ones in that particular case. But when we're talking about signed values, which, like I said, that's what this calculator works in, it's just perfectly fine, because that particular value in that case is actually a -1. So 0 minus 1 is -1. So that representation works really in both ways. But now there are actually different instructions for doing signed versus unsigned calculations. And that's all we have for today.